Hello and welcome back to Linear Algebra. Now, we've already reached part 23 and here we will continue talking about the concept of linear independence. But before we start with this, I want to thank all the nice people who support this channel on Steady via PayPal or by other means. My supporters make it possible that all my videos are freely available for everyone, so thank you very much. Now, the topic for today is still the linear independence, and here we will talk about examples. For this, please recall that such a family of k vectors coming from Rn is called linearly independent if the linear combination for the zero vector is only possible with vanishing coefficients. This is a very important concept which we now can explain with examples. And there I would say, let's start with a very simple one. Namely, it's the one where the family just consists of one vector from Rn. And then, clearly, this short family here is by definition linearly independent as long as this one vector is not the zero vector. Because then, in this case, to get this linear combination to 0, we have to scale the one vector with the scaling factor of 0. Moreover, with this example, you also see having the zero vector in the family changes a lot. Or more concretely, we would say such a family can never be linearly independent. It's always linearly dependent because the factor in front of the zero vector does not matter. So for example, in this case here, we could choose lambda 1 as 1. And then you see we have a non-trivial linear combination for the zero vector here on the right hand side. And there you see, this is all one needs for a proof of this fact there. Okay, there we had two general abstract examples, so let's go to a more concrete one. Therefore I would suggest first choosing an example with vectors in R2. So you see we have three vectors with two components. And now the claim is that all the three vectors together in one family are linearly dependent. To show that, you have to give a non-trivial linear combination for the zero vector. Indeed, here it's not so hard, because we can just take the vector 1, 1, then subtract the other one, so 0, 1, and the other one, 1, 0. Hence, we have scaling factors 1, -1, and -1. In fact, here you can already see that such a linear combination with three vectors in R2 should always be possible. However, before we do that, let's first look at another general example. There, let's consider the canonical unit vectors e1, e2 and so on in Rn. And the family should consist of all of them, so we have a family with n vectors. Here I can tell you this is one of the most important examples because it's the canonical example of a linearly independent family of vectors. However, it's not hard to show that this is indeed true. So let's just start with an arbitrary linear combination lambda j ej. And this one should be equal to the zero vector in Rn. Now, obviously at this point we should use how the canonical unit vectors look like. They have zeros and ones as components, and therefore we get a vector with lambda as components. More precisely, this one here is simply the vector lambda 1, lambda 2 and so on. And now the right hand side says this is the zero vector in Rn. So you see, this is just another way of saying that all the components are 0. And now if we read this from left to right, we see this is exactly the definition of linear independence. Okay, now moreover, this also gives us another important example. Namely, we know what happens when we add any vector v here to the end of the family. Then we know we can choose the coefficients in front of the canonical unit vectors in such a way that we get a linear combination for the vector v. In other words, such a general family then has to be linearly dependent. Now, with these examples in mind, I think we can close this video with another important fact. So there I want to tell you how we can also characterize the term linear dependence. Therefore, for this, as always, let's take a set or a family of k vectors that come from Rn. And now we have an equivalence that this family is linearly dependent if and only if we find an index L, a vector VL in the family that we can omit without changing the span. There, please recall from part 8 that the span of a set of vectors is just a subspace generated by these vectors. So in other words, the linear combinations of these vectors span a subspace. And now the linear dependence of the family tells us that we don't need all the vectors to span the same subspace. Then we know at least one vector can be omitted, and this one should be VL. So in general, we write it in this form here, but you know also L could be 1 or k. Moreover, I can tell you this equivalence here is not hard to show. However, it explains why the term linear independent is so important. The point is, if the set, the family, is linearly independent, we cannot omit any vector without changing the span. So in other words, then we would have the most efficient way to describe a subspace with a span. And in fact, this is exactly what we need when we talk about a basis of a subspace. But this will be a topic for another video. Therefore, I really hope that I see you there and have a nice day. Bye.